Well, hi everyone, this is Bob the Science Guy, and today we're going to finish up Chapter 1 with the three methods of heat transmission. And those are conduction, convection, and radiant heat. Before we get into them, I want to answer a question that I asked in the last video. So as you may recall from the last video, we were looking at a situation where we had a glass of soda and we put some ice in it and calculated what the final temperature would be. And here's the equation that we used for it. We had the mass of the soda at 20 degrees, and we subtracted from it the heat of fusion of the ice, which was 18 grams. Now, as you may recall, in that particular case, we had 250 grams of soda at 20 degrees Celsius, and we added to it 18 grams of ice. To find the final temperature, we needed to take the amount of heat that was in the soda, subtract the amount of heat required to melt the ice, and then put that over the mass of the soda and the ice times the heat capacity of a liquid. Now, a couple of things that we have to look at. First of all, we melted the ice with the soda, and the resulting solution was all a liquid. Then what we did was we took the mass of that liquid and the heat capacity of the liquid to figure out what the final temperature was going to be. But the question that I had was, what if this value up here comes to 0 or a negative number? What is the resulting final temperature? Well, that's actually pretty easy if you think about it. What is the only time that you could get a 0 or a negative number up here? Specifically, let's look at a negative number. That means that there was not enough heat in the soda to fully melt the ice. And the resulting solution would be partially soda and partially ice at the melting point of the ice, 0 degrees. Well, enough of that. Let's look at the subject for today, which is how heat is transmitted. The first way that it is transmitted is through something called conduction. Now, this is the aluminum slide from one of my Picket slide rulers. It's made out of metal. It's aluminum. Now, if I were to heat this end of the piece of metal, what would the temperature be on the other end? And would the temperature be different based on how long I applied this heat? What if I heated this side of the slide rule? Would this side get hot? Again, this relates to how long it's heated in addition to the amount of heat applied to it. What if instead of using the aluminum slide rule, I used this wooden dowel and heated this end? Would this end over here get hot as well? Let's go ahead and have a look at the equations for that. Now, when working on a problem of this nature, what we need to know are three things about the substance, and we need to know the temperature differential. So the three things that we need to know about the substance is, first of all, what is the thermal conductivity of that substance? So for example, aluminum has one thermal conductivity, water has another. Thermal conductivity is in watts per meter degree Celsius. And recall that watts are joules per second. So now that we know that, we need to know the area that this heat is being applied. So for a window, this would be the area right here. For a rod, it would be the end of the rod. Then we have the thickness or the length. That's the thickness of the window or the length of the rod. They're both combined into what's called distance. And finally, we need to know the temperature at this side of the rod to begin with, and the temperature at this side of the rod, again at the beginning. Likewise, we could look at the inside of the window and the outside of the window. We need that temperature difference. Now, you can tell an awful lot about a substance by looking at its K value. So for example, water has a K value of 0.6 watts per meter per degree Celsius. How about down feathers or air or polystyrene foam? Notice how low these K values are. These are insulators. Now, if you come up here to a metal, look at aluminum, 220. Diamond is 2,000. Well, let's go ahead and have a look at the example from the book and then maybe put a couple of variations on it just for fun to make sure we understand how to use this equation. So the question that was put in the book is, say you have a styrofoam ice cooler that has a total surface area of 0.95 meters squared. And you put some ice in it, and you put it in a car trunk that's 35 degrees Celsius. The ice-water mixture in the cooler is 0 degrees Celsius. How much ice are we going to lose in one day? Okay, so here are our values. So the question is, how much ice will melt in 1 day, which is 24 hours, or 86,400 seconds? Now the K of styrofoam is actually quite low. It's 0.010, and that is watts over meters degrees Celsius. The area is 0.95 meters squared, as we mentioned. The thickness is 2.5 centimeters, or 0.025 meters. Outside temperature 35 degrees, inside temperature 0, and once again there are 86,400 seconds in a day. So here's our equation. The rate of transfer, which will be in watts, is K times the area times the difference between hot and cold, in other words 35 minus 0, over the distance or the thickness of the styrofoam. It's a very straightforward equation. And when you put the values right up here into this equation, you get out 13.3 watts. Okay, so what is that? That's joules per second. The next thing we have to do is we have to see how many joules in 24 hours. And the way that we do that is we take 13.3 and we multiply it by the number of seconds. That makes the seconds cancel out, and it leaves us with an answer in joules. And that's 1.15 times 10 to the 6 joules. So far, this is pretty straightforward. So again, that's 1.15 times 10 to the 6 joules. Now the next thing that we have to do is simply figure out how many kilograms of ice that will melt. And we divide it by the heat of fusion of 1 kilogram of ice, which is 334 joules. So since we're dividing this by kilograms, we can multiply kilograms up here. Joules will cancel. And what do we get? 3.44 kilograms. Very straightforward. Now, the next question seems to be needlessly complex, and I'm not a fan of needlessly complex questions. However, sometimes it's very important to demonstrate an understanding of what's going on, and sometimes those questions do get rather convoluted and complex. This is a case of that. This is a complex problem that just is needed to demonstrate really good understanding. Let's go ahead and go over it. Two metal rods. We have a steel rod and we have an aluminum rod. They're both 25 centimeters long and they're welded in the center. The diameter of the rod is 1 centimeter, which means the area is 7.85 times 10 to the negative fifth meters squared. The steel end of the rod is dipped in water at 100 degrees Celsius, and the aluminum end is dipped in at 20 degrees Celsius. Now the first question that we have to answer is, what is the temperature at the weld point, which is 25 centimeters from each end? So let's go ahead and see what we have. The K of steel is 80 watts per meter per degree Celsius, and the K of aluminum is 220 watts per meter degree Celsius. What else do we need? We need the distance. So it's 25 centimeters for each rod. So let's set up our basic equation. So the transmission for steel is 80 watts times the cross section over the length. And the transmission for aluminum is 220 watts times the cross section over the length. Now there's one more thing that we have to add in here, and that is the temperature. So what's the temperature change from here to here? So it's 100 minus T, because T is the temperature that we're looking for. And over here, what's the temperature change here? We go from T down to 20. Now, like our problem from last time, what we need to do is we need to distribute this and solve for T. Now, the key to it is we set them both equal to each other. We'll distribute these temperatures out and we'll solve for T. Let's go ahead and do that real quick. Okay, so I did the math. I'll let you do this on your own. But basically, all I did was I took the 80 times the 7.85 times 10 to the negative 5 and divided it by the length, 0.25 meters, and that gave me this value right here. And then that was multiplied by 100 minus T. I did the same for aluminum and multiplied it by T minus 20. I distributed it, put all of the known temperatures on this side and all the unknown temperatures over here, pulled out the T, and then I ended up with this equation down here, and the result is 41.32 degrees Celsius is T. Now the second part of the question is, what is the rate of heat transmission? Well, we recall from here that heat transmission through the steel equals the heat transmission through the aluminum. So all we have to do is solve for either of these. We know the temperature at the joint is 41.32 degrees Celsius. So the book uses the steel. I'll go ahead and do it with the aluminum. The PAL will be the K of aluminum, which is 220 meters degrees Celsius divided by 0.25 meters times the area of the tube, which is 7.85 times 10 to the negative 5 meters squared, times the temperature change, which is 41.3, which is what it is here, down to 20 degrees. And the 41.3 is from here, and then it goes down to 21 degrees, so that's our temperature change. And it works out to 1.47 watts. Now this is a rather complex problem. You need to keep track of your algebra, but it's actually pretty easy to solve, and it's kind of an elegant solution, so it's kind of fun to do. And whether you enjoy it or not, it's probably going to be on your test. You might as well learn it. Now before we finish this section, there's one other term that you may see on a test or have people talk about, and that's something called an R value. The R value is simply that fraction right there. It's what you multiply the change in temperature by to get the P value. So there's no great mystery to it. Now the next thing we want to talk about is convection. We transfer an awful lot of heat primarily by evaporating water. A good example of this is sweating. So let's say that the average human generates about 120 watts of heat. What is the mass of water that would need to be evaporated in order to dissipate that heat out into the environment and keep us cool? This looks like a pretty straightforward equation. We take 120 watts and we divide the latent heat of vaporization of water into that 120 watts, and that would give us the amount of water that we need to evaporate in order to get rid of that 120 watts. So the math for this is pretty straightforward. What we have is 120 joules per second, which is watts. And we take that and look at the number of joules per gram of water. Then the latent heat of vaporization of water is 24,030 joules per second, per gram, excuse me. And that equals 0.0494 grams per second, or multiplying that by 60, we get 2.96 grams per minute, or about 180 grams per hour. Now this evaporation can occur as sweat or through our lungs, and that's a very doable amount. Now as much as I hate to do this, this video is getting a little bit long. The final method of heat transfer is by radiation, and that uses something called the Stefan-Boltzmann law of radiation. It's kind of complex. I'm going to refer you to the book to kind of go over it. I think at this level, as long as you're given the equation and you're given the constant, I think you can probably get through this on the test. Your body is radiating heat off, so P will be negative because you're expressing heat. You're not receiving heat. Heat goes from hot to cold. So just remember, it's cold minus hot. Good luck on this one. So this is Bob the Science Guy. Thank you very much for stopping by. I hope this helped you out a little bit to get through Chapter 1 of University Physics 2. Take care.